This is Professor David J. De Los Reyes. Good afternoon, guys. Okay, let's proceed for this afternoon. I have a new topic this afternoon. Okay, let's proceed. I am now on lesson number 80 on my channel on the topic Integral Calculus, subtopic volume, under Miscellaneous volume. And the topic for this afternoon will be the solid cube. We will derive the formula for taking the volume of a cube, okay, using miscellaneous volume. Okay, I will try to read the problem. Derive by integration the volume of a cube of side S. Meaning, if we are given a cube, it is something like that. The side is S. Okay. Cube is actually a solid thing with all the dimensions equal. Meaning the first side is S, the second side is S, and the height is still S. It's a cube. Actually, we will be deriving the formula volume is equal to S cube. So the formula for taking the volume under solid mensuration under lower mathematics is actually volume for a cube is actually S cube. And that actually originated from integral calculus. It was derived from integral calculus before they pass it to the so-called solid mensuration topics. It was derived from integral calculus. Okay, let's try to proceed. We try to graph the cube on the XYZ plane. So this is the y-axis, x-axis, this is the axis. We are now on a space. Okay. We are now on a space. Okay. For the meantime, we assume we are on space. The first page is actually the XY plane. The next page is actually the YZ plane. And the bottom portion is actually the floor section. It is actually the XZ plane. We are now on space. Okay. So if we try to place the cube on the XYZ plane, the configuration will be something like this. This is side S. This is side S. This is side S. This is side S. S, 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 S. Okay? And even the height is still S. Okay? So if we try to place the proper coordinates, considering for the meantime, sorry guys, I will get my piece of paper. Okay? Considering for the meantime the XY plane, this should be S0, this is SNS, the one at the origin will be 0, 0, and this point here is actually 0S. Okay? And if we try to consider the Y, and Z axis, this should be S0, this is SNS. Okay? The more complicated one is actually this point here. Because this point does not lie on the XY plane, it does not lie on the YZ plane, but it is on a space. Okay, it is within a space. So actually the coordinate of this one is actually SSS. Okay, this side is S, this side is S, and this side height is S. So if we try to bring out the coordinates of this point here in space, it will be S, 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 meaning the value of X is S, the value of Y is S, and the value of Z is S. It is in space. Okay, let's try to draw the differential area. The differential area will be this, covered by this, by the one red and mark. Okay, this horizontal slice, horizontal slice, horizontal slice, horizontal slice. So actually, to integrate the volume, we must have to move this differential slice here from this point here up to this to cover up the total cube. This is the differential slice. This side here is CL minus CR. This side here is XR minus XL, and the thickness is dy. This portion is actually this. Okay? And this portion here is actually this. The one in red. And the thickness is dy. So I draw a corresponding figure here to bring out the relation. Considering the XY plane, this is the horizontal slice. And the length of this, okay, this one here, the one at the back. The one at the back. It is actually the difference of XR minus XL. So I place it here with an arrow. This length here is the difference XR minus XL. And on the other side, on this portion here, considering the Y and Z plane, okay, this is the differential slice. This is ZR, the one on the right. This is CL, this is the value of Z on the left. And actually this length here is actually CL minus CR. Okay, it is this. Okay, so you can actually try to, what you call this, imagine that this XR and XL come from this, and this CL and CR come from this, considering the YZ plane, and for this one, considering the YX plane. So if we try to take the volume, take this area here, times thickness. So differential volume will be XR minus XL quantity times the quantity CL minus CR times the quantity dy. In here, XR is actually a vertical line. Okay? And the equation is XR is equal to S. The abscissa on the left is also a vertical line. And luckily, it coincides with the y-axis. So the equation is actually XL is equal to 0. Considering the YZ plane, this is a vertical line also. And the equation of this is ZR equal to 0. It coincides with the y-axis. Okay? And this side here is also a vertical line. It does not coincide with the y-axis. Its distance from the y-axis is actually S. So the value of CL is actually S. So if we try to substitute the value of CL, CR, XR, and XL back here, it will be the quantity S minus 0 times the quantity S minus 0 times dy. So the resulting differential equation for the volume for a cube will be S squared dy. Then try to integrate both sides. Try to integrate. The integral of the differential volume equal to the integral from 0 to S of S squared dy. We are following this. The integral of differential volume will be volume equal to S is constant, it comes out, so it will be S squared, and the integral of dy will be y with the limit from 0 to S. Volume now will be S squared times S, okay, minus 0. Upper limit, lower limit, but the lower limit has no effect on the final formula for the volume, right? So volume now for a cube will be S squared times S, and actually volume for a cube, as a general equation, is actually S cubed, cubic units. So actually, the formula we are using under lower mathematics, under solid mensuration, volume for a cube, for any cube, will be the side of the cube to the third power, cubic units. Okay guys, that's the derivation of the formula of a cube using miscellaneous volumes under integral calculus. Okay, good afternoon, Los Angeles.